Alright guys, welcome back. This is going to be an interesting question from the second chapter of the Mechanics of Materials, question 55, and we have two steel bars that we have the information about the elastic modulus and the coefficient of thermal expansion, and they are used to reinforce a brass bar, which is the orange bar that's in the middle of these two plates in order to reinforce the brass bar. And we have also the elastic modulus for brass, also thermal coefficient, and we have a force of 25 kilonewton that is applying on two ends of this. And we know when the steel bar or fabricated distance between the center of the holes that were to feed on the pins made of 0.5 millimeter smaller than the 2 millimeter needed. So what happens in here is that we have the brass bar in the middle that has two holes. I'm just drawing the what we see if we look at it from the top side. So this is the brass, and also we have two steel bars here too, which is the top and bottom, and those ones are the holes are a little bit like if I show something exactly same as the brass. So these are actually a little bit closer, and like obviously there's one at the top, one at the bottom. And look, I'm detaching each of these. So, and actually this one is same as that one. So what we're gonna do is that we're gonna put this steel bar, we're gonna heat it up to a certain temperature, and what happens is that this hole are gonna move 0.5 meter, the distance between the center. So this would go along the holes that are already inserted in the brass. So once the steel bars are heated and the holes are aligned with the holes in the brass, so the pin is gonna go through this. So after this, the temperature is gonna be dropped back to room temperature, which means these two holes are trying to shrink back to where they were. And that's gonna create a force in brass and the steel. But the A part of the question is, before getting to that, is asking how much increase in temperature required to fit the steel bars to the pin. So for that, we have our thermal deformation, which we show it with delta T, and it would be the coefficient times the temperature difference and the length. Since in here, we're not gonna heat up the brass, it's only the steel parts that are gonna go, and this will be the bottom steel. So the question is asking for this temperature increase, and we know that our deformation is 0.5 millimeter. We have the coefficient of this steel is 11.7 times 10 to the minus 6. The temperature difference is what we are trying to find out, and the length is basically the length that we have between these two, the center of the holes, which is 2 meter. So we have millimeter in this side, meter in this side, so we're gonna do 10 to the minus 3 just to be consistent with the unit. And since our coefficient is based on 1 per centigrade, so the delta T that we get in here would be also in degrees C. So let's just calculate this. So we're gonna have a ratio 0.5 times 10 to the minus 3, and in the denominator 11.7 times 2 times 10 to the minus 6. This is gonna give us 21.37 degrees, and this is the answer for the A part of the question. So in the B part, the question is asking for the stress in the brass bar after the load is applied to. So as we can see, obviously we have the external force P, and on top of that, we have another force. We can show it with F, which is coming from the shrinkage that happens once the temperature drops. So once the temperature is dropped, what happens is that the pins are trying to pull the steel bar. Same in here, same in here. And one assumption that we need to take in this question is that the pin is going to be a rigid pin, so there wouldn't be any deformation, so it's not going to get like that. So we are assuming that the pin is a rigid pin and it's not going to deform. So based on that, whatever force that is applying in here, obviously we have the same thing at the bottom, we can call that force F. It's going to make a compression force on the brass. And if we just call this one F brass, this one F steel. So because we have our equilibrium equation, if we just write down the forces for this bar, we have 2Fs minus Fb is equal to 0. If we just do sum of all forces in X, let's just call this our X. Fb is equal to 2Fs, or we can just consider this force as a net force of these two, and we call it F, and that would be equal to F brass. So from now on, we're just going to go with the force F, which is going to be the force that is applying on the steel bars and the compression force that is applying to the brass. So let's go from there. So we're just going to consider, as I mentioned, we're just going to consider one single force, F, to the brass, and another force to the steels, half of that value. So we're going to have a deformation because of these force on each of them. And on top of that, we have another external force, which makes another stress on these bars. So the final stress that we're going to have at the end would be the stress that is coming from the force P. So I'm just going to show it with sigma T, which would be the sigma is coming from, or the stress that's coming from the force P, and also the stress that's coming from the force F. That's what the question is asking us. And we are only interested in the brass bar. So we're going to find it for the brass. But now the main thing in here is how we're going to find this F. So one thing that we know in here, because these plates or these bars are attached with the pins, their deformation would be the same because they are moving with each other. So whatever delta that we have for S or steel is going to be equal to what we have for brass. And now let's figure out what's the deformation in this steel. So first of all, the deformation that steel is going to experience is because of that shrinkage, which is a negative value. I'm going to show it with delta S because of the thermal or the cooling down of the steel, which tries to shrink it, so it has to be negative. On top of that, we have the force F that is making a tension in the bars. So this one, since it's elongated, it will be positive. And I'm just going to consider one force F for two of them. So FL over the area times the elastic modulus, all of them are for steel. But one thing that we need to keep in here is that the area that we have is the area of the two slabs, because this force F is the net of these two. Or we can just pick one of the forces and go with the area of the half. So that's pretty much everything for the deformation of the steel. We also have the formation of the brass. There is no thermal expansion for brass, but as I mentioned, the brass is in compression in here, which means it will have a negative elongation. And the elongation would be because of that force F. So F, length of brass, area of the brass, and the elastic modulus of brass. So as I mentioned, these two values are the same. And what we found for the deformation of the thermal expansion, it was basically that 0.5 millimeter. So if we just put these two equal to each other, what we're going to get is that the delta or thermal expansion of the steel, which again we know is 0.5, is equal to the elongation of steel because of the force F plus the elongation of the brass. Actually, the shortening of the brass because it's in compression, AB times EB. And as I mentioned, we know this is 0.5 millimeter or 0.5 times 10 to the minus 3 millimeter. And from this, everything is known other than F. So we should be able to find the force in here, and as long as we have the force, it's easy enough for us to find the stress. And we just have to watch for the areas in here. So let's just show what's the area of this steel. So the area of this steel, since we took the net force, the force F, we are dealing with two areas, one in here and one in here. So we have these two rectangles where one side is 40, the other side is 5. So the area would be 40 times 5 times 2, since we have 2. So this is going to be 400 millimeters squared, or 400 times 10 to the minus 6 meters squared. And the area of the brass would be, I'm just going to clean up the figure. So the area of the brass is this rectangle here. Again, one side is 40, the other side is 15, and that's pretty much it. So 14 plus 50, this is going to be 600 millimeters squared, or so we have the elastic modulus for each of them. The length also for both of them is the 2 meter that we have. So they're gonna have the same length, 2 meter. So we just have to plug in those numbers in here, and at the end of that, you're gonna get force F 8.8112 times 10 to the 3 newtons. So just keep in mind that all the elastic modulus are in gigapascal. So you just have to do, for example, for steel, 200 times 10 to the 9 Pascal, and same for the brass. So if you want to find the stress of the force F for brass, as we talked about, the brass is actually in compression, so it will be negative. The force over the area, the force is 8.8, 11, 12, 10 to the 3, and the area we figure out, the area of the brass is 600 times 10 to the minus 6. And let's just calculate this. So that's gonna be 14.685 megapascal, and negative sign, but it's not over. Still, we have to find the stress because of the force F. And now we can move on to the stress that is applying to brass because of the force F, because of the force P. What we need to figure out in here is that the force P that is applying in here is consists of the force that is in steel and the force that is in the brass, right? So that's one thing, one equation that we have. So our P is equal to the force that is generated in the steel and also the force that is in brass. So one equation is that. The second equation, again, all of these are pinned together. So the slabs that we have are attached with these pins, which means their deformation is the same. So we can just call the formation of steel is equal to the formation of brass. Again, very similar to what we had in the previous step. And this is the force P. And this is going to give us, also we're going to go with our equation, the force PL over area of the steel, elastic modulus of a steel is equal to P brass L, area of the brass, and the elastic modulus of brass. Now we can cancel out the L here, and now we can find the relationship between PS and PB. So basically our PS would be AS ES over AB EB times P of the brass, and we just have to plug this in into the previous equation. We know our total P is 25 kilonewton, or 25 times 10 to the 3 newtons, and that should give us both PS and PB. If you just plug PS in here, we will have one equation with only PB as unknown. So if we do that, our PB will be 11.014 times 10 to the 3 newton. And once we have that, we can find PS. That's going to be 13.986 10 to the 3 newtons. And obviously, one thing that we know in here that the deformation that we have in here, because they are pulling the two sides of this bar, the elongation here is positive, so they're both in tension. So since we were interested in the stress in brass, here we're gonna have force of the brass over the area of the brass. The force is gonna be 11.114 10 to the 3 newton over the area. Again, we have the same area for the brass, which was 600, same thing that we did in here. And we were talking about the normal force, so we care about the cross section that is perpendicular to that force. So 600 10 to the minus 6 meters squared, and this is gonna give us 18.357 10 to the 6 Pascal. So again, this is the stress in the brass because of the force P. So that's why we show it with P. And the total stress that we were talking in this question is the stress of the brass because of the P and the stress of the brass because of F. So we figured this one's negative value, and we found that this was 18.357 10 to the 6 Pascal. And what we found for F, so this was one of our value, and the other one was what we got in here, minus 14.685. So as the final answer, 18.357 minus 14.685. The total stress of the brass would be 3.672 times 10 to the 6 Pascal, or 3.672 megapascal. And that would be the final answer for this question. Hope everything was clear. Let me know if you guys have any questions. And you guys take care. I'll see you in the next video. Have a good one.